Okay, good morning. Week 11. So we have 2 more weeks to go, excluding this one. Let's talk about term test 2 correction. So term test 2 correction will occur tonight, okay, from 7 to 9:30. C Avenue to learn for location. I could not remember which room I booked. I'm very sure it's in T13, okay, the temporary building 13 that is on Main Street West. The questions for term test 2, for those of you that need to do the correction, are exactly the same as what you have written a week ago. Okay, so the questions are exactly the same. Okay, on that. Anyone, any questions so far? Anyone? Okay, I don't hear anything. So today's agenda will be design of a transmission shaft. Okay, so I've not completed the theory yet. Okay, so let's recap where we did to on Friday. So on Friday, I explained why tau max is used, okay, and why we use tau max. Okay, because most material will fail based on shear first, because the magnitude is lower. Okay, we have a lower magnitude. Then we were deriving our tau max relationship to our sigma m and sigma shear exact. Okay, so just to quickly recall, where sigma m. Okay, so I'm going to start from equation number 3. I'm going to take this whole thing. Okay, and I'm going to bring it over here. So this equation is true, and it's only true when there is no axial loading. Okay, when there's no axial loading. And this equation, again, is only true when you have stresses acting like this. Okay, if you construct your element of a shaft, okay, your stresses can only have this sort of stress field distribute or stress being applied. Okay, so you have one stress in either compression or in tension, and in the other direction, there's no stresses at all. And you have stresses in your shear. Okay. So from here, our bending stress M is our stress induced by the bending moment, is equal to my over I. Okay. Then our shearing stress is equal to Tc over J, right? Where C is the maximum radius of the shaft. Okay. Another thing I like to add in, where there's no axial load and the shear stresses induced by shear force are small when compared to those induced by the torque. So you can see that we ignore VQ over what? IT. Yes or no? Okay. So now we start putting everything into equation number 3. So therefore, tau max is equal to, so I'm going to put everything in now. So my over 2I squared plus by TC over J squared. Okay. Then from here, I'm going to put note, because we are dealing with a shaft, okay, where we have J is equal to 2I. Okay. So J is the polar second moment of area, and I is just our second moment of area. Okay. So knowing that, we can replace the entire equation of tau max is equal to my over J, right, squared, plus by TC over J squared. Okay. Then I want to draw your attention to the shear stress distribution, the normal stress distribution and shear stress distribution. So what we are dealing with now is a shaft. Okay. This is the cross-section view of a shaft. Okay. So we know that being in a shaft, so these are two of axes. This is our Y and Z, for example. So this is a cross-sectional view. And I'm going to sketch the distribution. Okay. So this is our, it can be our normal stress, or it can be our shear stress. This can be our Y, or this can be our C. Okay. So in terms of normal stress distribution, we get a profile, something like this. Okay, this is just a sketch. Okay. So this is our normal stress profile, and this is correlated to my over I. Okay. So at this point, our magnitude Y is equal to our magnitude C. Likewise for this point. So minus Y is equal to minus C. So in terms of shear, this is how our shear stress will look like. Okay, I'll try to make the gradients different, or not I'll be in a lot of trouble. So this is our shear stress distribution. Okay. So this is our TC over J. So what I'm trying to highlight is this, is tau max or sigma max, right? Sigma max. And then you have your tau max, right? Sigma max and tau max occurs when y is equal to c, or c is equal to y, and c is the radius of the shaft. Okay. So coming back to our equation over here, right? We can also write where tau max, so therefore tau max is equal to mc over j squared plus by tc over j. So I replace the y with c because both of them are the same magnitude when it's at its maximum, either maximum normal stress or maximum shearing stress. Okay. Then I can bring this out where we have c over j square root of moment squared plus by torque squared. Okay. And note, okay, moment is equal to moment in the y direction squared plus by moment in the z direction squared, and torque is acting on the x-axis. So when I rewrite the above equation, tau max is equal to c over j. So it's my squared plus by mz squared plus by tx squared. Then from here, we can find our j over c. Okay, so this is equal to my squared plus by mz squared plus by torque squared divided by tau max. Okay. So tau max over here is the allowable shear stress from material mechanical property. Okay. Now for a circle or for a shaft, right? I forgot the formula for I, okay? I'm going to look for it. Pardon me, okay? I should be more prepared. I can't remember now. So that's where the formula sheet comes in, I think. I hope you bear with me. There's one, there's two. And if we were to look at the formula sheet, right? So is pi over 4, pi over 4, r to power 4. So pi over 4 radius to power 4. Okay, so that's I. So we know that J is equal to twice of I. So this is equal to pi R4 over 2. Okay. So we know that R is a radius. This can also be put as pi C4 over 2. So we have pi C4 over 2, right, divided by C, and this whole thing over here is your my squared plus by mz squared plus by tx squared over tau max. So you can get rid of this This is a power 3. So therefore, C is equal to 2 over pi. Yeah, 2 over pi. Then you still have the same. The rest is still tau max. My squared, mz squared, torque in the x direction squared, power of 1/3. So this final formula is used to find the radius allowable radius. Okay. You will see this formula a lot in